Data poisoning is one of the most relevant security threats against machine learning. Many applications, from image classification to speech recognition to spam detection, rely on untrusted training data. An attacker can craft malicious samples and inject them into a dataset to degrade the performance of machine learning models that are trained on that dataset. Recent work has shown that denial-of-service data poisoning attacks are highly effective and that there is a need for new defenses against this threat. Hello everyone, my name is Simon Roschmann. I'm an undergraduate computer science student from the Technical University of Munich. During my internship at Fraunhofer ISAC, the Institute for Applied and Integrated Security, I worked together with my fellow researchers Nicolas Müller and Konstantin Böttinger on a new approach of detecting denial-of-service poisoned instances. Our defense is based on extracting information from the training data in a very generalized manner so that we can identify poison samples based on the information that is present in the unpoisoned part of the data. Let's start with having a look at related work. Denial-of-service poisoning attacks aim at maximally degrading the performance of a model to make an application or service unusable, for example, a spam filter. The evaluation of poisoning attacks against support vector machines, regression algorithms, and against algorithms for multi-class classification has demonstrated significant threats for systems that rely on collecting untrusted data. To mitigate the threat of denial-of-service poisoning attacks against spam filters, there has been an approach to measure the impact of each training sample on the classifier's performance. This defense can effectively determine samples that decrease the accuracy and should be discarded. However, it is computationally expensive. A similar but more efficient approach was based on influence functions. There were also different approaches of outlier detection and clustering. These approaches highly depend on the selection of appropriate thresholds, and they suffer from the curse of dimensionality. This means that the sparsity of data in high-dimensional space makes the search for similarity based on metric distances complicated. The contribution of our paper is a new defense against strong denial-of-service poisoning attacks. This approach is based on the re-evaluation of training samples by the poison classifier. We try to leverage information that is present in the unpoisoned part of the dataset to identify and remove poisoned instances. And this approach overcomes difficulties of previously proposed defenses. Our defense is not susceptible to the curse of dimensionality, and it is not dependent on arbitrary threshold selection in contrast to outlier detection. Our approach keeps false positive rates and false negative rates low. In comparison to related work, we improve false positives and false negatives by at least 50%, often more. Now I'd like to present two denial-of-service poisoning attacks from related work against which we evaluated our defense. Let's have a look at the threat model. Denial-of-service poisoning attacks aim at violating a system's availability, which means that they aim at making a machine learning model inconsistent or unreliable. We distinguish here between limited knowledge attacks and perfect knowledge attacks. Limited knowledge attacks simulate a more realistic attack setting because the training data or learning algorithm is unknown. Perfect knowledge attacks simulate an attacker that knows everything about the targeted system. These attacks can be used to derive estimates of the worst-case performance degradation. Usually we assume that a dataset is crowdsourced and that an attacker can introduce a certain percentage of adversarial data points into the training dataset. These poison samples should not take extreme values to be more difficult to detect. As a baseline attack, we consider random label flipping. The attacker selects a maximum percentage of instances at random from the training dataset and changes the labels to a class that is different from the original one. Of course, this is a limited knowledge attack because it only requires the attacker to have access to the labels of the training data. But we also evaluated our defense against the current state-of-the-art attack for denial-of-service data poisoning. This is now a perfect knowledge attack on multi-class classification. In contrast to random label flipping, backgradient optimization attack also changes the features of the poison samples to increase their impact on the degradation of the model, and that's why the backgradient optimization is highly effective compared to the limited effectiveness of random label flipping. The two equations at the bottom show that finding a set of poison samples, dp star, that maximizes the attacker reward A is a B-level optimization problem. Problem 2 is called the inner problem, and it describes the training process. So when a model is trained on benign training data and malicious poison data, it is the aim to minimize the overall model loss L. Problem 1 is called the outer problem. It depends on the model parameters that are found during training. And the attacker here aims at creating poison instances, dp star, that maximally degrade the model performance. So more precisely, when a model is trained on these poison instances and on the benign training data, the attacker objective function A should maximize on the validation dataset. For denial of service poisoning attacks, maximizing the attacker's objective function A is equivalent to maximizing the model loss L. So every poison sample is initially assigned a class different from the original label. Then the attack repeats poisoning steps that modify the features of a malicious sample to increase its impact on the degradation of a model. Every poisoning step computes the gradient of the attacker objective function A with respect to a single poison instance. And this gradient describes how we have to change the single poison instance to increase the attacker objective, respectively the model loss. For more details on the math behind this attack, I'd like to refer you to the original paper of the back gradient attack. Here we only give a visual example of this attack in 2 figures. They depict a data set with 3 classes, shown as the blue, red, and green dots, over a 2-dimensional feature space. The black crosses represent a single poison data point over the course of 26 attack iterations. And this poison sample is created by taking a legitimate data instance, flipping its label to a poison label. So here we have this flip from 2 to 1, from green to red. And then we iteratively move this sample to a region of higher validation loss and lower validation accuracy. The effects of training a model on the normal data plus a single poison instance is shown by the background color map. The x1, x2 coordinates represent the coordinates of the poisoned instances. And here we partition the x1, x2 feature space into a grid. We then train a model for each poison instance on that grid, and we plot its validation loss and accuracy. So this gives us the ground truth with respect to how the poison sample should be changed in order to be maximally effective. We can see that the attack modifies the poison point such that it is moved to a region of higher validation loss in the left plot and to a region of lower validation accuracy in the right plot. After presenting 2 attacks from previous work, it's now time to present our contribution. The new defense is designed to identify poison samples in a dataset without knowing the poison rate. It only requires the model and the poison dataset. Both is of course available to a defender who is training a machine learning model. This is the most unrestricted input we could think of, and it ensures that our defense can be used in any real-world setting. The system pipeline was inspired by previous work from my fellow researcher Nicolas Müller on detecting mislabeled instances in classification datasets. Let's go through the algorithm here step by step. We are given a dataset that consists of n instances out of C classes. The input x represents these n data instances, while target y represents n data labels as one hot encoded vectors of length c due to the C classes. There can be poison instances in this dataset, but these instances are of course unknown to the defender. We then train a model M on the dataset, and we use this model to reclassify the training input x. Then we obtain the new class probabilities y prime. Now we calculate for all instances the label likelihood Ln that instance xn is assigned the original label yn. We compute these label likelihood values with the inner product of yn and yn prime. Then we sort all training instances according to these label likelihood values in ascending order. And this yields a figure that is presented here on the right. The x-axis represents the single instances, while the y-axis shows the label likelihood values. And the blue line here demonstrates that we sorted these poison instances according to their label likelihood values in ascending order. Instances with small label likelihood values with respect to the original label can thus be found on the left end of the plot. We then determine a threshold to distinguish between the wrongly labeled poison data and the correctly labeled benign data. And we find the threshold by approximating the first derivative of label likelihood values over a sliding window. We then simply choose K as the argmax. We remove instances that are left of the cutoff point from the training set, and we then retrain the model on remaining data right of the cutoff point. Of course, these steps can be applied iteratively until convergence. For instances with small class probability, the classifier considers the original label extremely unlikely based on the feature distribution learned during training. And this approach works because there is still a significant majority of unpoisoned data in the training dataset. This is again a reasonable assumption for crowdsourced datasets because a malicious individual can only introduce a small portion of malicious data. The model M must be able to generalize well and not overfit the dataset so that deviations from the overall distribution of a class can be easily found. Neural networks satisfy these requirements, of course, and to prevent overfitting, we used an aggressive learning rate and early stopping. To evaluate our defense against the label flipping and backgradient attack, we chose 7 numerical image datasets that are presented in the table here. We have the breast cancer and spam-based dataset. These are 2 numerical datasets that consist of 2 classes. We have the points dataset, an artificially created dataset with 3 classes and a 2-dimensional feature space. You could already see them in the heat map plots. And we have image datasets. They are subsets of the original MNIST and Fashion MNIST datasets with either 2 or 3 classes. Poison instances are later sampled from the validation set at runtime. Our main model is a neural network with one inner layer that consists of 10 neurons, and this is appropriate for our small datasets of maximum 300 training instances. It's also in line with related work from the backgradient poisoning attack. For the image datasets, we performed these experiments with a 2-layer convolutional neural network. Now we present the results of the data poisoning attacks on our datasets. We injected up to 10% of poison data and averaged all results over 5 individual runs. The results for an exemplary dataset, the spam-based dataset here, are shown in these 2 figures. The x-axis represents the increasing poison rate when adding more and more poison instances into the training dataset, and the y-axis shows the test loss in the left figure and the test accuracy in the right figure. The orange and blue lines visualize the trend of the test loss and the test accuracy for the flipping attack and the backgradient attack, and these vertical lines show the standard deviation. The 2 figures demonstrate that both attacks are effective and that the backgradient attack outperforms the more naive flipping attack. An individual breakdown of the results for all 7 datasets has confirmed that finding. Now I'll continue with the evaluation of our defense. The figures here give an example for applying our defense with 2 steps on the MNIST 1.7 dataset. Each image shows a knee-plot of label likelihood values sorted in ascending order. You have already seen these kind of plots before. The x-axis lists the sorted instances, while the y-axis shows the corresponding label likelihood values. Remember that this label likelihood denotes a likelihood of the instance being assigned the original label. The red line represents the true fraction of poison samples. Here it's 10%. And the green line represents the fraction that is estimated by our defense algorithm. This estimate is selected as the highest increase in label likelihood values over all instances. Our defense is accurate in estimating the poison rate. Have a look at the picture on the right where the red and green line even overlap. So after finding the green threshold in the first step in the left figure, we train a new defense model on the data right of the cutoff. We then calculate new label likelihood values that you can now see in the second plot on the right. These are calculated for every sample, not just the training samples, and then we sort every sample again according to their new label likelihood values, and we find the second precise cutoff in the right plot. We apply our defense to 2 scenarios: data poison with a label flipping attack and a backgradient optimization attack. This table here presents the results of our defense against the backgradient optimization attack on a neural network with one inner layer. The values are averaged over 5 runs. False positives, FP, correspond to the non-poison samples that are left of the threshold that our classifier wrongly assumes to be poisoned, and they will be discarded from the training dataset. False negatives, FN, correspond to the poison samples that are right of the threshold that our classifier wrongly assumes to be benign and that will remain in the training dataset. And the datasets contain 10% poison samples each. The column nu hat shows the poison rate that is estimated by the defense algorithm, while the next two columns compare these false positive rates and false negative rates of our defense against a random baseline. We identify poison instances with an average false positive rate and false negative rate of 0.02, and that significantly outperforms a random baseline where both false positive and false negative rate are 0.09. The test loss and test accuracy improve considerably when using our defense on the poison dataset. Have a look at the mean values here. We achieve increasing the test accuracy from 0.89 to 0.94. To show that our defense is not specifically tailored to a given learning model, we perform the same experiments with a convolutional network instead of a dense network, and we obtain similar results. We also provided an evaluation of non-poison models to demonstrate the utility of our defense, and in the presence of no poison samples, our method only discards few samples of low label likelihood with a minimum effect on the loss and accuracy of the model. These ROC curves demonstrate the successful ordering of training instances according to their label likelihood values. The curves were averaged over 5 runs, and we got them by applying our defense on 7 datasets poisoned with a backgradient optimization attack. We go through the sorted instances from low label likelihood values to high label likelihood values, and at varying thresholds, the x-axis presents the fraction of false positive samples, in this context benign data, while the y-axis presents the fraction of true positive samples, in this context poison data. The rising true positive rate on the left shows that many poison instances are among the first instances in a sorted array, and that low label likelihood values are obviously a good indicator for poison data. The random baseline here in gray is consistently outperformed. We implemented 2 popular approaches for data poisoning detection from related work and compared their results to our defense. These approaches from reference 18 and 19 are based on different outlierness scores. They use the k-nearest neighbor algorithm with the L2 norm or the local outlier factor, and they also differ in their selection of thresholds. We observed that all of these methods suffer from the curse of dimensionality, since they are based on a metric distance in high dimensional space. The table here shows that our proposed defense obtains significantly lower false positive rates and false negative rates. The mean row shows mostly 50% lower false positive, false negative rates for our defense, often even more, and you can see that our algorithm performs especially well for high dimensional data, such as image data from Fashion MNIST or MNIST datasets. Let's come to the conclusion. Our new defense against denial of service poisoning attacks can detect and discard malicious instances from a classification dataset, either by selecting a threshold automatically, as we showed with the knee plots, or by sorting the instances for efficient triage by a human expert, as we showed with the ROC curves. Previous work has mostly used clustering and outlier detection against poisoning attacks. We re-evaluate the training samples by the poison classifier. That's why we can avoid the curse of dimensionality and why we have the chance to come up with automatic threshold detection. The experimental evaluation on 7 high-dimensional datasets has shown that label flipping and backgradient optimization attacks significantly degrade the performance of neural networks. But with our defense against datasets with up to 10% of poison samples, we could demonstrate the reliable identification of malicious instances. Across all datasets, our defense achieved low false positive and false negative rates. These rates were 4 times lower than the random baseline, and in comparison to related work, we achieved false positive rates and false negative rates that were 50% lower. We identified 2 main possibilities for future work. First, the system could be tested against more datasets and more poisoning attacks, and second, our defense could be evaluated on a wider class of machine learning algorithms. Thank you very much for your attention, and come visit us in Munich in the future.